Hello dear student, myself Dr. Sarika Kalra, Associate Professor from Ajay Kumar Garg Engineering College. This is my lecture 6 on, I am taking the subject of electrical machine and this is lecture 6 and in this lecture we are going to discuss about the how to determine the equivalent circuit parameter of the transformer. As we seen in the last lecture, I have discussed about the equivalent, how to draw the equivalent circuit of the transformer and how to draw the phasor diagram of the transformer and what is the significance of this equivalent circuit. So, in the last lecture, we have seen that we have discussed the exact equivalent circuit as well as the approximate equivalent circuit and how this parameter will taken toward to the refer to the primary side or refer to the secondary side. So, this is RC, XM, R2, X2 that we have seen, that is this is the exact equivalent circuit of transformer. We have discussed like this is R1 is the equivalent to the winding resistance in the primary side, X1 is the leakage due to this leakage reactance in the primary side of the transformer, and these parameters are due to the secondary side. And this branch is equivalent to due to this magnetizing current, because the flux is depend upon the voltage, flux is fixed, but due to this reactance present in the transformer, and the transformer has the material has the permeability is not infinite. So, there is a requirement the current is there, that requirement of the current is the magnetizing current. So, this term this term is due to the this term is present, this reactance is present due to this magnetizing current. Okay. And this is the core loss component which is also there in the transformer, because of the core loss present in a practical transformer, the core loss present in the transformer core. Okay. So, this is the exact equivalent circuit that we have already discussed in the last lecture, and after that we just approximate that that equivalent circuit by shifting the no load branch to simplify the circuit. So, either we shift this branch towards the primary side or we shift this branch towards the secondary side. By using this, we can approximate the circuit so that the circuit become less complicated and the analysis become easier. This is RE1, this is XE1, where RE1 is the R1 plus R2 dash and XE1 is equal to X1 plus X2 dash, or we can write this equation in this manner, like RE2 is the R2 dash plus R1 dash plus R2 and XE2 is equal to X2 plus X1 dash. That means these equivalent resistance is referred to the primary side, impedance refer to the primary side, and these impedance refer to the secondary side. So, where this R1 is the resistance in the primary and R2 dash is the resistance of the winding of the secondary side of the transformer, refer to the secondary side, refer to the primary side. Okay. So, this we have already discussed. Now, the approximate equivalent circuit is like this. This is the approximate equivalent circuit, where we don't denote any the primary and the secondary, we just denote this, the circuit is become RE and XE. And if we denote by 1 and 2, that gives the refer to, either it is, if it is RE1, that means all the parameters are, RE1 is referred to primary side and XE1 is referred to 1 stands for the primary side. And if this RE1 represent by RE2, that means the resistance is referred to the secondary side. So, that already we have discussed in the last class. Now, today lecture we will see the how to determine this parameter, the equivalent circuit parameter of the transformer. So, to determining this equivalent circuit parameter, we perform two tests. One is the open circuit test and the short circuit test. And we also will see later we will see that how the open circuit test and short circuit test perform, and how this test is performed in a particular side. So, this we will see later. So, how to determine the equivalent circuit parameter? This is done by a two test. This is done by a performing the two test. One is the open circuit test, second is short circuit test. Okay. So, today's lecture we will see how this open circuit test will perform. Okay. So, in open circuit test, the connection is, by using this open circuit test, you just experimentally draw this circuit So, this open circuit test, just remember this is test, as the name suggests that it is open circuit. So, this test is always performed at open circuit. That means there is a no load in the other side, there is no load. The circuit, the I2, the load current will be 0, there is a no load, it performed at no load, no electrical load. That means the load current is 0. And second thing is that it is performed at a rated voltage. Okay. And third point, it is always performed at a low voltage side. And why it is performed at a low voltage side, we will see. Okay. So, there is no load, the current is, the I2 is 0. So, this is the connection diagram of the the open circuit transformer in the two winding. So, if you apply this voltage V, this is the auto transformer, this is the ampere, the ammeter which are using to measure the current in the open circuit test. This is the wattmeter connections MLCV, this is a wattmeter, and this is a 2-winding transformer on which we perform the open circuit test, and here we connect the voltmeter. And this test is always performed at a rated voltage. Okay, this you have to must be remember that open circuit is performed at a rated voltage. Second thing, it is the open circuit, that means the secondary is open, there is no load in the secondary side. Okay. Third point, it is always performed at a low voltage side. Okay. And why this is, we will see. So, when we apply the rated voltage here, the current start flowing, because there is a no load here, only the magnetizing current is flow, only the exciting current is flow in the transformer. So, the emitter gives you the exciting current. Okay. And this wattmeter gives you the power and the voltmeter give you the voltage reading. Okay. So, in this case, this wattmeter, and if it is open circuit, what is the kind of equivalent circuit? We will see. If it is open circuit, the equivalent circuit at open circuit become this. If you draw the approximate equivalent circuit, it is like this, but there is a I2 is 0, so there is no meaning. Only this will here, and it is performed at a rated voltage. Okay. So, the equivalent circuit at open circuit test become this is the equivalent circuit of the open circuit test. Now, according to that, you can draw also the phasor diagram at open circuit test. So, this is flux because you are applying the rated voltage. So, the flux is produced because this magnetizing flux is depend upon the voltage only. Okay. So, to produce this constant flux, there must be the requirement of the magnetizing current. Suppose the magnetizing current is Im, okay, and the core loss component is also there because it is a practical transformer, it is not an ideal transformer, it is a practical transformer. Must be a core loss, and which is in phase with this voltage. So, it is suppose IC, the core loss component. The sum of this IC and Im become the IE, that is exciting current. Okay. And here is the rated voltage here, because the voltage is always 90 degree leading with the flux, and the EMF induced by the transformer is 90 degree lagging with the voltage, lagging with the flux that we have already seen. If you say like phi is equal to phi m sin omega t, then E is coming about minus n d phi by dt. So, it is coming about phi m sin omega t minus pi by 2. So, that is why the RMS value of the the voltage is, the induced voltage is always lagging with the flux phi m. So, E1 is the EMF induced in the primary winding and E2 is the EMF induced in the secondary. So, both EMF is lagging behind the flux phi m, and this voltage is always in equal and opposite to the this EMF induced, because it must satisfy the KVL. So, this is the phasor diagram of the open circuit test. Okay. So, this V is equal to minus EA, and here this IE is equal to IC plus IM. Okay. Now, suppose the power factor at no load is theta 1, suppose, or theta 0 you can say. Okay. So, from here you can write this IC is equal to IE cos theta 0, and this IM is equal to IE sin theta 0. Okay. So, now if we go in the previous slide, this is the open circuit test connection. Okay. As we see that this perform at a rated voltage, now when you set up this open circuit test, you will find the 3 readings, that is ammeter reading, the wattmeter reading and the voltage reading. So, how this, using this reading, the voltage and ammeter and wattmeter reading, how we will find the parameter of the equivalent circuit, the transformer. So, as you seen that in open circuit test, the circuit become like this. So, in this case, with the help of this open circuit test, you will get 2 parameter, the XM and this RC parameter. So, here suppose from the setup, of OC test, open circuit test, we got the current, the no load current, the ammeter reading. The ammeter reading gives you the no load current, that is, suppose this is IE. Okay. And the voltmeter reading is V, and the open circuit is test performed at a rated voltage. So, this is the rated voltage. Okay. Third, you will get this power wattmeter reading, that is, suppose V0. So, what is this power? This is a power, or you can say it is a voltmeter reading. Wattmeter reading. And this give you the V I cos theta 0. If the power factor is, the no load power factor is cos theta 0. So, wattmeter gives you the power, that is V0 is equal to Vi cos theta, because it is an open circuit. So, the all power consumed in this circuit only. So, it can be written as W0 is equal to Vi0 cos theta. Okay. From that you will get this cos theta 0. because you know the wattmeter reading from the setup, you know the rated voltage and you know the rated, the no load current. So, from that you will get the cos theta 0. Okay. Now, from if you find this cos theta 0 from the setup, this will show that the I is equal to I cos theta 0 and Im is equal to I sin 0. So, from that you will get also the magnetizing branch, that is from that this I is equal to IC is equal to IE cos theta 0 and IM IE sin theta 0. Okay, because IE you know, cos theta you will know, and from that IC is equal to I cos theta 0 and IM. Now, from this circuit you will see that the voltage appear across this parallel branch is the rated voltage. Okay. So, from that you will see that the Xm is equal to V by Im. So, from that you will get Xm is equal to V by Im, and this RC gives you the RC is equal to V by IC. So, from that open circuit test you will find the no load parameters, the no load branch parameter, that is Xm and the core loss component. Okay. This Xm is equal to V by M and RC is equal to V by M. So, how we what we conclude from this open circuit test? We see that with this open circuit test, we find the parameter, we find the no load parameter, that is Xm and RC. And in this case you just see that this wattmeter gives you the power which is consumed in the at no load. That means, and it is performed at rated voltage. So, because it is performed at no load, the current is only the magnetizing current, and in transformer the magnetizing current is always 2 to 6% of the rated current. Okay. So, in this case you see, if you consider the resistance in the primary, there is a drop, there is a power loss in the primary, that is I square R1, but due to this current, the no load current is very small, we can neglect this power loss, because in this circuit the power loss is due to this R1, the resistance in the primary, and RC, the core loss component. But this I is so small, the exciting current in the transformer is 2 to 6% of the rated current. So, it is very small. So, the power losses through this resistance R1 and RC is very small. So, we can, and Second thing, one is the power loss due to this R1 and RC is very small. Second thing, this test is performed at a rated voltage. So, the core loss power, the core loss is due to like core loss is proportional to the voltage square, because as you see that the core loss is what is core loss? It is sum of the hysteresis loss. Suppose this is hysteresis loss plus your eddy current losses, and this hysteresis loss, if you see, that is F times of Bx times, plus it is proportional to F frequency and the flux density, and the eddy current loss is proportional to the flux square and Bm square. So, this flux density is nothing but proportional to the flux, and this flux is generated with voltage. So, flux is proportional to the voltage. Okay, that means this core loss is proportional to the V square times, and here it is coming like V 1 minus x times of. So, that means your core loss is proportional to the voltage, and this open circuit test is performed at a rated voltage. So, we can see that we can neglect this I square R loss in comparison to the core loss, because power I square R loss due to this resistance R1 RT is very small, because it is performed at a no load. Okay. And also it is performed at a rated voltage, and the core loss is dependent upon the voltage. So, we can neglect the I square R losses in comparison to the core losses. So, this wattmeter gives you the second thing, you see that this wattmeter gives you the core loss power. Okay. So, from that test we can conclude this open circuit test is, first thing is performed at a no load, second it is performed at a rated voltage, and it is performed at always at the low voltage side. Okay. So, this is the circuit diagram of the no load circuit, and we conclude that with the help of this open circuit test we can find the parameter, no load parameter of the transformer like Xm and Rc, and we also get the power, which is only we can assume that this power is the core loss power. Next we will see the short circuit test in the next coming lecture. Thank you. If you have any query, you can contact me on this email ID. My email ID is kalrasarika@ajaykumargarg engineering college.ac.in. Thank you.